To write an arithmetic series using a sigma or a summation notation, we need to come up with a unique quantity that could describe each of the term in that series, and that would be the quantity that we are going to pair with the summation notation. Take note that the sigma notation is also known as this notation, commonly known as a summation notation, with a specific quantity here where that given quantity contains a movable or running value for n, which starts from 1 until the n, which is infinitely. Since it's called, uh, we have here a given that we have an ending series, infinite series. So that's why we are until n. So we're looking for that unique item here, quantity rather. But first, let us try to determine whether these examples are really arithmetic series. To do that, let's try to determine whether the difference from term to term, those terms separated by addition, follows a unique common difference. From 2 to 3 in number 1, we increase by 1. From 3 to 4, we also increased by 1. And from 4 to 5, we also increased by 1. Therefore, the difference of the common difference for the terms in this series is 1. And with that, we are assured that number 1 is an arithmetic series. For number 2, from 8 to 6, we decreased by 2. From 6 to 4, we also decreased by 2. And by 4 to 2, we also decreased by 2. Therefore, the common difference is actually decreased by 2 or by subtracting 2 per term. This is also an arithmetic series. In number 5, it may look like too complicated, but if you're going to write 5 and 6 as the integers with denominator 2, you will see that 5 is actually 10 halves and 6 is actually 12 halves. This would mean that we could actually see that from 10 halves to 11 halves, we increased by 1 half. From 11 halves to 12 halves, we also increased by 1 half, as well as from 6 or 12 halves to 13 halves. Our common difference here is actually 1 half. But definitely, we did not write 10 halves and 12 halves since we need to simplify terms if possible. And finally, for number 4, we could see that from negative 2 to negative 6, it gets lower or it decreased by negative 4 or by 4 points or negative 4, as well as 6 to 10, negative 10 and negative 10 to negative 14. So the common difference is also negative 4. So with this common difference from items 1, 2, or 3, we have shown that they are really arithmetic series. But aside from that, these common differences are actually helpful for us to identify the unique quantity to be placed here. As I have mentioned, that unique quantity, should represent each term of this series, but not the sum yet, because the sum is already shown by the sigma notation. Okay, we'll have another situation with that soon. So to do that, we are going to look for the representation for a sub n. Since we are talking about what would be the representation for the quantity that would represent, or a representation for each of the terms. So generally, we know that it's a sub n. And for arithmetic series, or arithmetic sequence rather, a sub n is computed by a sub 1 plus the quantity n minus 1 times d. This is the formula in getting the nth term of an arithmetic sequence. Why is it that we are moving away we are combining sequence and series? Because as you have already know, a series is just a summation of all terms in a sequence. So an arithmetic series is where we added up all terms in an arithmetic sequence. That's why we have this. We need to come up with that quantity to be placed here. So let us try to substitute here the values for the a sub 1, the first term, and the d, but not n, since we need to come up with a quantity that could represent all terms. In that case, a sub n here, which is also supposedly the term to be represented here, is given, may be given as a quantity 2 plus n minus 1 times 1, which is your D. We need to simplify it. So you will have here 2 times, plus rather, n minus 1. And finally, the term that could or the quantity that could describe and all of the terms in this series is n. 2 minus 1 is plus 1. This is the quantity that could describe all terms in this series. That's right. When n is 1, 1 plus 1, 2. That's correct. When n is 2, 2 plus 1, 3. When n is 4, 4 plus 1, I sorry, when n is 3, rather, the third term, 3 plus 1, 4. And when n is 4, or the fourth term, 4 plus 1, 5. This quantity can represent each of the terms here. And with that, this is the quantity that we are going to place here beside this summation notation. Since it doesn't end, you have n starts with 1 to n, and you will have here n plus 1. But wait, it's not yet correct. Why? Because if we are going to treat it like this would mean that we are adding first all n from 1 to 10, from 1 to n rather, and then we simply add 1 in the end. We need to make sure that the quantity should stay as quantity. So that's quantity of n plus 1. We need to place here a parenthesis. This is this the arithmetic series given here in summation notation that could describe all of the sums here in any n you want. This is the process for this practice exercise. Let's proceed to number 2 and use the same process. Again, you have your formula. A sub n is equal to a sub 1 plus the quantity n minus 1 times d. So a sub 1 here, the first term is 8 plus n minus 1 times 2. As we continue with this, let me have here separate space. You will have 8 plus 2n minus 2 as we distribute this inside. In number 1, we were not able to distribute because that's just multiplying by 1. Here, all right, sorry for that. It's negative 2. Let me correct myself. It's negative 2. So when we distribute this, we will have negative 2n, and then we have plus 2. Again, it's negative 2. I'm so sorry. And then you will have here negative 2n, 8 plus 2 is positive 10. This should be the representation of all terms here. Let's try. When n is 1, 1 times negative 2, that's negative 2 plus 10, you will have 8. That's correct. When n is 2, 2 times negative 2 is negative 4 plus 10, that's 6. When n is 3, 2 times negative 2 times 2 is negative 6 plus 10, 4. And then, just for the purpose of checking, when n is 4, 4 times negative 2 is negative 8 plus 10, you'll have positive 2. This is now the quantity that we need to place beside the summation notation where n starts from 1 to n. You will have here, again, parenthesis is very important, negative 2n plus 10. Or if you don't, you may also, if you have planned to add first 8 plus 2, you could also have this form, alternate form, 10 minus 2n, as n starts from 1 to n. Just like here, when I said I will add first 8 and 2, and I will get 10 minus 2n. They are just the same. In number 3, it may be a tricky one since d is 1/2, but still we just need to follow the given equation. A sub n is equal to a sub 1 plus n minus 1 times d. And then you will have here, since we could use 5, we can let's just stick with 5 plus, or later you could still use 10 halves as we combine everything later. So you have n minus 1 times 1/2, which will yield 5 plus 1 half of n minus 1 half. Okay? More or less, when we're going to have 5 as 10 halves rather, you will have a result of 1 half n um, plus 9 halves. Where did I get 9 halves? Again, 5 is 10 halves minus 1 half. You will have 9 halves. So this is one of the possible alter forms. So you could have the summation where n starts from 1 to n of the quantity 1 half n plus 9 halves. This is the first form. Or if you don't like too much fractions, you could also have this alternate form. Pardon for this. You'll have, you may factor 1 half if you want to. When we factor 1 half, let me have a better spacing here, right? Just like that. You will have here the summation. When we factor 1 half, you'll have 1 half of n plus 9, where n starts from 1 to n. Okay, we factored 1 half so that we have n plus 9. Or another alternate form for this is the for the law of some the rules for writing summation notation. This is a constant. You could have here 1 half of the summation notation of n plus 9 as n, sorry, n starts from 1 to n. I have these three forms, but if you would like to stick with this, it's still okay. Let us try to check whether this is really correct. When n is 1, okay, that's 1 half times 1, okay, so 1 half, plus 9 halves, that's 5. When n is 2, that's 2 halves, plus 9 halves, that's 11 halves. When n is 3, that's 3 halves plus 9 halves is 12 halves or 6. And when n is 4, that's 4 halves plus 9 halves is 13 halves. That would mean this is correct. And any of these alternate forms are also correct. In number 4, our last item here, still, we have a sub 1 plus the quantity n minus 1 times d. A sub 1 is negative 2 plus n minus 1 times that common difference, which is a negative 4. So you will have here negative 2, multiply that, you have plus negative 4n, and you will have here plus 4. And finally, when you would like to arrange it, you have negative 4n, negative 2 plus 4 is positive 2. Now, this is the quantity that should describe all terms here. Let's try. When n is 1, 1 times negative 4 is negative 4, plus 2, you will get negative 2. When n is 2, 2 times negative 4 is negative 8, plus 2, you will have negative 6. When n is 3, it should become negative 10, okay? Negative 3 times, 3 times negative 4 is negative 12. Plus 10, that's why you will, plus 2 rather, you will have negative 10. And finally, when n is 4, negative 4 times 4 is negative 16, plus 2, you will have negative 14. And this is again what you're going to place here for your summation notation. Pardon. You have the quantity negative 4n plus 2, where n starts from 1 to n. This is how we write this arithmetic series in the use of the sigma or the summation notation. You may review this as part of your preparation. See ya.